Hello, everyone. Welcome. Thank you for joining me. Say hi in the chat. It's good to see so many of you in the chat already. BZ, Syra, AKB, Nader, John Remy. Thank you all for joining us. And Mom, of course, everybody's favorite, our all-star, our perennial all-star. If you're new, as always, feel free to say hi. Let us know where you're coming from. Although if you are new, you're really kind of getting in on this towards the end, since this is our last stream in Programming for Lovers associated with our Python stream. We've come such a long way. It's hard to believe. We've been through it in Pittsburgh. We've been through a lot of seasons. I remember we had feet of snow outside at one point in time, and it was so cold that it was just unspeakably cold. Now we've flipped that entirely. So it's been a journey just in that regard. I remember then I got sick, and it seemed like I was sick for about a month, but we got through it. And one thing I want to do is just to kind of reflect here is if you've been with us throughout a lot of this, or especially through part 2 or wherever you've been, wherever you started, I think it's an opportunity to say, look, we've covered a lot of ground here in the last few months, and it's an opportunity to kind of stand on the mountaintop, whatever the mountaintop for you is, and reflect and look back and see where we started. So I thought it'd be a great chance for me to just ask you, what are the things, big picture things that you've learned? When you look back down the mountain, what are the things that you can do now that you couldn't do before? And what are the things that you appreciate about computer science, whether that's just in general or with respect to its applications in science, that you have learned through the course of doing this? Let me know in the chat. It would be good to know. Constantino, welcome. Roy, great to have you as always. As you're telling me, coming up with some things of what we're reflecting on, I'll just say thank you so much to everyone who has joined us. Everybody who has joined us, whether it's just once or throughout the entire series. I cannot say thank you enough for just sticking around with us, because we've spent months on this, and we've had some streams that ran pretty long as the course of that. So I truly and truly appreciate you joining us for any amount of time that you were here. It's been great. It's also kind of a bittersweet end, right? We're finishing something up, but it's not goodbye. We have more Roslyn streams coming. We're just over the halfway mark on all of the Roslyn streams that we want to do. We have our Vibe Coding Studio class, which is starting June 22nd. We're going to be putting out more announcements and videos and stuff like that around that over the coming weeks. That is for our Fail Math subscribers. So there's links in our description. If you'd like to join us for that course, great. The more the merrier. And towards the end of the summer, early fall, we're going to start our Great Ideas in Computational Biology course. So we're going to have that coming. And there's going to be even more. So I can't wait for all of that. Even though we're closing kind of one door this evening, we've spent a lot of time in the room. And it's an opportunity for us to move into some other areas, which I'm super excited about myself. And I hope you are too. We're going to finish up assembly language and Xtoy tonight. And I'll also point out that we're going to make some deep points and have some reflective moments. At least I hope. I hope we're going to have some deep philosophical points that we're going to make. And we'll do all that after we have an opportunity to do a little bit closing for our assembly language topics here. Remember, you always remember structured procrastination. That's good. Yeah, it's honestly, and as just another plug for our kind of mini AI course on how to use it effectively. That that's the kind of framework and top-down thinking and learning how to delegate. It's kind of, even though we're in a brand new era of like chatting to a chatbot and learning how programming really means this transformation towards like prompting something or telling kind of a worker that you have access to, that you're managing, how to go about solving a problem. The same type of thing applies even in that context. We'll save that for another day, but it's nice to see these ideas kind of appear in what seems like initially it's killing programming, but actually it's just enriching and broadening what we can do with programming. And that's a great example of something that we see in that context. All right. Sorry, thanks for the kind words. Well, yeah, I would say post to our Discord. Let me know. You're always welcome to just shoot me a message on LinkedIn or email me or whatever. And just if you have like a testimonial or this sort of thing, these are the types of things that are really helpful. So if the course has meant something to you, please don't hesitate to reach out to me. This is, we probably will send an email around about that, but these are great opportunities for me to just kind of know what your point A and what your point B was, regardless of what that is. You could have solved every exercise in the entire course and done a project in both parts, but you don't have to have done that. If there are things that kind of helped you appreciate certain things around the intersection of computing and science, let me know. It would be great to know. Okay. So the stuff we're going to do, which is finish up our assembly language module here, probably doesn't seem like it's tremendously connected to a lot of the modern stuff that's going on that I've talked about with respect to our new course and with respect to prompting and AI and chatbots and all this sort of thing. But I would say nothing could be further from the truth. So we're going to see that when we get to the very end of what we're doing this evening. We're going to see that even though this, we're working at the level of binary, that this stuff is inherently connected to the most modern computing frameworks that we have. So you'll have to sit tight for the end of the stream in order to kind of see that connection, but that's where we're going to get. We're going to start here with building two GCD algorithms, starting with this trivial approach, which is an approach that you might apply by hand, and then transitioning over to this beautiful Euclid GCD approach that we have seen all the way back to the start of the course. So the course is kind of making a big loop here. We started with, looking at Python and seeing how Python could implement these ancient mathematical algorithms from Greece, and how, even though these problems seemed like they might be easy to solve, we needed clever algorithms in order to solve them efficiently. And so we saw that in the context of GCD algorithms, and we saw that in the context of prime finding algorithms. So how this is going to work is I'm going to show you the demos here for our GCD algorithms. And then if you would like, we've got practice exercises allowing you to do the exact same thing for a straightforward prime finding approach. You're going to be amazed that it fits into one Xtoy program. And then you can generalize that to Civ Veritasthenies. So what's nice is we'll even be able to store all the different prime numbers in the memory, and our practice exercises walk you through that. So take a look at those if you'd like to have kind of the full experience. From my perspective, it's almost like a little bit cathartic. I would even say it's thrilling to go back and say, well, this was the start of the course. We learned about, from the context of a very modern programming language, how to do this. And we're going to delve even deeper into the computer, and we're going to see that the exact same ideas come into play. For example, something like structured procrastination or modularity, or these types of ideas, they're still going to be at hand when we implement these on the level of assembly language, which is pretty neat. And so I'll let you do that if you want to. We are nearly ready to start. I think I would point out, as a very brief refresher of our Xtoy assembly language, we've got a lot of ground to cover, so I won't spend a lot of time on this. But I do want you to remember that in this virtual computer that we're working with, and you may be very familiar with this from our past streams. This might be the first time you've seen it, and that's okay. I think that regardless of where you are, I think there's something to appreciate here. But the idea is that we're going to represent a program as a collection of these 4 hex digit strings. And so this is a powerful thing. Like, the program is just a collection of a bunch of integers. And we'll see that when we take this journey to our dark heart of computer science. And with respect to these strings of 4 hex digit strings, the first digit always represents the operation that we're interested in. So if we see a 0, we see that that means regardless of what follows it, regardless of the 3 remaining digits, then that, when executed, when encountered as part of the program, means to halt. The first 6 integers correspond to arithmetic and logical operations. So 1 is add, 2 is subtract, and then we saw these other operations, and, XOR, shift left, and shift right, and we connected those to arithmetic operations too last time. We're really probably going to mostly just need add and subtract, but the other ones are there if useful. 7, 8, 9, A and B. Remember, A is 10 and B is 11 because we're in hex. These represent the idea of loading in values or loading them from the memory, or taking a value that might be in a register, one of these kind of special addresses that we have that are close to what we're working with, and then pushing them to store them back to the memory. Remember, there's a special memory address, FF, which is our final memory address in this virtual machine, that if we read from it, that's like standard in, so it's like taking a value from the user, and if we store to it, well, that's like printing a value to the console. So we're still going to be able to do these types of things that we've seen at the start of the class, but the way that the program runs is it looks at our memory, and the idea of the memory is, the program starts at line 10. All these elements of the memory could store values as well, or they could have the program, and the program starts off at line 10, then it goes line 11, 12, 13, and so forth. But then there are special commands, C, D, E, and F, that allow us to branch. So we can test if a register is 0 or if it's positive, and if so, we can jump it to a specific location, or we can just jump to a value stored in a register. And then the final thing we saw, which allows us to really essentially implement functions, is to say, remember where you were, and in the meantime, jump to some other location that's stored in a particular register and carry on there, so that when you return, the function returns to the register that you stored that bookmark in. And so that allows us to essentially kind of make a loop and come back to where we were. This is an idea that when we implement our GCD algorithms here, is something that we're really going to apply and see quite a bit, because, as I said, we're going to see multiple functions, we're going to see modularity, and so we're going to need jump and link. That's going to be, from many perspectives, our most important command of all. But we're ready to start. As always, please like and subscribe if you'd like deeper connections. Join our mailing list, join our Discord, all that good stuff so you can stay in the loop. And we're ready to go. Let's code. All right. And I should say one more thing. There's going to be as many as any other stream. I actually have a lot of opportunities to ask you questions. So this is technical stuff with Visual X Toy, but I'm still going to ask you questions in the chat. So please feel free to interact. Let me know if you have any questions, and we'll get started. All right. We're going to start with a program or a file called trivialgcd.toy. It's an XToy program, and it's going to compute the GCD of 2 integers using a trivial approach, which sounds a little bit mean, but this just really means the approach that we might come up with to solve this by hand as the first idea we would have. And this is something that takes us back to the very start of the class. We have pseudocode here for it. And the idea is Give me 1 second. Okay. So the idea of our algorithm is we're going to set m equal to the minimum of our two input integers. And then we're going to range a collection of, some integer p between 1 and that min, and we're going to continually check. Is it the case that the current integer, is a divisor of both of our input integers, a and b? If we ever find a hit, so every time we find a divisor, we're going to keep updating the value of d that we have equal to p. And the idea is we're just continually checking whatever that we see. So that's the pseudocode that we see. Give me 1 second here. Having just a couple of technical difficulties, but we're good. Okay. All right. So the idea here is with any program, a lot of the things that we want to do is all about like writing a main. So we're going to have a main with our trivial GCD, and that's a natural place to start. So I'm going to have I'm going to call it function main in the same way that in Python it's def main. So we're thinking about the code that we're running as a function. And I can even say what I want to do with this. I'll say we want to, input or read two numbers from standard in. We're going to compute their GCD and write to standard out. And main is always going to start at a special memory address. So we're going to indicate that the starting memory address is 10. And when we're at 10, the first thing that we want to do is we want to read in two integers from the user. So I'm going to store those into registers 1 and register 2. So I'll have A1FF and A2FF. Remember, if I read in something from FF, that's like capturing a value from standard in or from the user. And the 1 here, or the 2, indicates that I'm storing this into these special addresses called registers, and I'm storing it in register 1 as well as register 2. Register 0, there is a register 0. The language reference tells us that always stores the value 0. We're not going to change it because sometimes you're going to need the value 0 so frequently that it's like set as a permanent constant. Then what we'll do, one more thing I might do, and this is kind of a bookmarking measure, but the last thing I want to do is accidentally overwrite one of the numbers that I have. So this number is going to be our A. This is going to be our B. And let's store those two into special addresses that we know are not going to change in the RAM. And I'll do that into memory addresses 0, 1. And I'll do this in memory address 0, 2. So this one stores A in memory of 0, 1. And I'm just going to add a comment here. And this stores B in memory address 0, 2. And once we've done that, I know that they're safe. I'm never going to overwrite those values, but I might overwrite registers. And what I want to do is to say, we want to call a function. And now we learned last time, we can call a function in our next line of code. We can call a function with the jump and link command. We need to represent the next kind of hex digit is going to tell me which register do I want to store the bookmark of where I need to jump back to. So that's going to be in register F. It's going to remember that I'm here, so I'm not going to lose my track of where I am. But in the meantime, I'm going to jump somewhere else. And that place that I'm going to jump, I'm going to put it at line 20. So down here, we know that line 20 is where our trivial GCD function is going to start. And so this is our function call. And when we call this function, the next thing that we want to do is to say, well, if I make it here, I know that the function has finished. And I know also that if once the function is finished, one of our registers presumably stores that GCD that I care about. So it's got to be somewhere. I need to agree on where it is, and I need to remember this when I write the function. I'm going to assume that it goes into register 6. Okay, there's nothing special about register 6, but that's the one that I've chosen for this. So if I know that it's after calling this function and after this function finishes, if I know it's in register 6, I'm going to print it to the console. I know how to do that. I can store register 6 to the special address FF, and this is going to print our value. And then finally, if we make it here, we're just going to halt. So this is end of program. And that's going to be like natural, normal behavior. It's exiting normally, nothing wrong with that. But then the idea of def main, or however we're thinking about it, this is the main part of our code. All it does is reads two things in, calls the function, prints the value, and halts. And that's good. This is the type of thing that we've seen going back to the start of the course in Python. We're just seeing it reflected in a much lower level language here. But the idea that I want you to take from this is the language itself doesn't really matter. We're still seeing kind of good programming principles at play, one of those being modularity. And that means, well, the first thing that we want to do is to say, if we're remembering modularity, we're remembering top down. I can think, well, I might need a function min2 that's going to take the minimum of 2 integers. Maybe that function is easier for me to write, but that's not where I really want to start. Where I really want to start is with this trivial GCD function. So that's the function that I care about the most, and that's where I should start. And I'll have a function then that's called trivial GCD, and I should be nice and specify its inputs and outputs. So the idea here is we don't really have function signatures with like type hints and these types of things. So I need to be nice to the user and specify register 1 is equal to A, register 2 is equal to B. So we knew this when we called this function here. Registers 1 and 2 stored A and B respectively. And then our output, remember I said we needed to agree on what register it goes into. So register 6 is going to have GCD of A and B. And then we're going to have a return address. And the return address that I said here was when we called the function, we said register F is going to get where the program counter was. So that's my bookmark. The return address is going to be when the function is finished. I'm going to jump back to register F. And then I'm going to have some temp variables. And this is a little bit of a cheat. You would need to sit and actually work this out to figure out exactly where your temp variables are going to be. I'm going to say there are R4, R5, R6 is technically a temp variable. It's just going to be where the GCD gets stored. R7, R8, and R9. We might have more, but I think that's probably it. Here's a good opportunity for me to ask you a question, which is, why do I specify these temp variables? Like, what is it? The idea is that through the course of the function, these are the registers that I'm going to modify. So they're going to hold these values that might not ultimately be useful. The only one that's ever going to be kind of output by the function is this register 6. But I'm going to set register 4 or 5 or 7 or 8 or 9. And I'm curious, why would I specify that before I even write any code? Why is that a useful thing to do? Why would I do such a thing? I guess I don't have to. I could be mean. Why would it be mean not to specify that? Yeah, a lot of good thoughts here. And I think there's multiple possible valid considerations here. But yeah, John, the one I like is, so the system doesn't overwrite those memory addresses. Or what this function is telling me is, look, register 5 is going to get overwritten. So when you called this function, if register 5 was storing some value, right, and then you call when at this point in time, register 5 had something. What this is saying is register 5 will get overwritten. So you need to remember where it is by placing it somewhere in the RAM, because the function is going to set register 5 equal to something else, which we're going to see. So that's an important thing to do as part of good practice in this kind of make-believe assembly language, but it's still very relevant. Okay, so let me show you the function itself. And with a lot of this, I will try to move reasonably quickly through it so that, we're not getting bogged down in assembly language. Is the assembly language itself the real kind of important thing that I want you to take away from this? No, what I want you to get is a flavor for that we're still doing programming. At whatever level of programming we're at, from this level all the way up to AI, there are still kind of principles that we're going to follow. And so the first thing I'm going to do then is, let's first off set d equal to 1. So I can set d equal to 1. Remember, register 6 is what's going to store the GCD. Here's our pseudocode. I'm setting d equal to 1, which is what I'm going to return. I probably should set register 6 then equal to 1. So this is going to store our GCD eventually. And then, well, the next thing I'm going to do is call the min function. Why? Because that's what we do in the subroutine. So we're going to have yet another function here that I'm going to call, which is going to be a min function. I need to, agree that it goes somewhere. And let's give ourselves plenty of memory here. I'm going to say line 2.1 is going to be F, which is jump and link. I don't want to use register F as my return address because I already have a return address here. I could do it this way, but it would mean that I would have to store it somewhere in memory. That's going to get tricky. It'd be much better if I just use one of my temporary variables. So I'm going to call the min function by remembering where I am by holding this bookmark in register 7. And in the meantime, I'm going to jump somewhere. And I'm going to make a note to myself that the min function will go at address, and we're just going to move it somewhere, 50. Okay, so F750 is going to call this min function and remember where I was in register 7 and then come back. Okay, one thing that I might do, in this case I don't have that much code going on, but I think it's probably good practice, is once I've called that min function, I know the minimum of these two numbers, I'm going to snapshot the minimum into memory somewhere. So I'll store this by saying 9403, 9403. And so that says register 4, which is going to be the return. So the output here is register 4. Okay. And that's where the min is going to be. So once I have computed the minimum, at this point in time, I'm assuming that it's in register 4, and I'm placing that into memory address 03, so that now this permanent memory contains A, it contains B, and it contains the minimum of A and B at memory address 03. So that's the other use, like the nice thing about starting your program at 10, because it means any kind of variables like this that you want to have around for a little bit of time, you just put them in the memory at 01, 02, and so forth. Once I've got that though, I'll say, well, we want to have our loop. So if we think about our loop, we're ranging an integer p between 1 and m. And so if I want to do that, a great thing I probably should do is to start p equal to 1. So p is going to go into register 5. There's no rhyme or reason for that. I just need to, understand that that's where it's going to go and make that decision. But I'm going to set register 5. I can set a register with 7, register 5, and I'm going to set it to the value of 1. So register 5 now gets this value of 1. That's good. So the idea is I need to have some loop process, and every time through the loop, I'm going to add 1 to p, and in order to add 1 to it, I'm going to have another special register, which is just going to be equal to 1. So register 8 is a constant. Just a minor note to myself to say, this is never going to change. Register 5 is going to change. Every time through the loop, I'm going to be adding to it. Register 8 is not going to change. It's just going to be a constant. And now we're going to say we can start the loop. So the key point is, how do I know when the loop is over? And the loop is over when P becomes larger than M. Okay, so when we have a for loop, this is how I wanted you in whatever programming language you're working on to think about the for loop. You set P equal to 1, you keep looping. Every time you execute all of the code in the block, you add 1 to P, so it's 2, and then you go through it again, and then it's 3, and you carry on until such time as, well, if you're ranging between 1 and M, until such time as P becomes equal to M plus 1, and then you stop the loop and you carry on. So at one point in time in everybody's journey in programming, that's a complicated idea. And now at this point in the course, I hope it's something that you're comfortable with, but the idea is we're just seeing it one level lower. So if P is greater than M, we need to be a little clever about doing this to remember that P greater than M means that P minus M is greater than 0. And we say that because, well, we have a control command that's able to check if a register is positive and take some action based off of that. So we're going to remember that, and then we're going to use it. So what I want to do next is to make the subtraction. So I'll say 2954, which says register 9, another temp address, is equal to the difference between register 5 and register 4. So register 5 was P, as we saw here. This was our P. And register 4 was equal to the minimum that I said. So the output of the minimum function is going to be at register 4, so this is our P minus M. And register 9 is just going to store that. And we'll see that we're going to come back to this line, but for now, register 9 just equals this difference, P minus M. And then we want to say, is it the case that P minus M is positive? So we're going to make our check. I can do that with branch positive, which is Command D. So I'll say check register 9. And if register 9 is positive, well, I want to jump to a particular address. And the idea is it's not clear at all what that address should be at this point in time, where I'm going to make this jump if register 9 is greater than 0. So one of the things that I might do is just to leave that. I could tell you what the address is going to be, but it's also going to probably seem a little bit mystifying to you if I just enter the value. You'd say, well, how would you know to jump there? And the idea is that you wouldn't. And so instead, I'll leave that open. And what I'll do is to say, at this point in time, we are now in the loop. And the reason why is that this will, jump over the loop if P minus M is greater than 0. So this is our jump, and if I don't jump it over the loop, then I'm inside of the loop. So at this point in time, at line 27, I'm inside the loop. And if I'm inside the loop, then we need to say, well, what is it that we're going to do? Inside of the loop, we check, is P a divisor of both A and B? And if so, I'll set D equal to P. So I need to check each of these two possible statements one at a time. So we need to check if P is a divisor of both A and B. And we can't check them both at the same time. We're going to need to make one check, and then if it survives that check, we're going to make the second check. So first, we check A. So we're going to say 27 is just 1150. And what this says might look different to what this is. This says add setting register 1 equal to register 5 plus register 0. So technically this is register 1 equals register 5 plus register 0. But remember, that's a plus. But remember that register 0 has this special address that always just reads 0. So it's really just register 1 is equal to register 5. And so we'll see this quite a bit. If you ever want to set one register equal to the value of another one, well, you might say that doesn't occur in our instruction formats. And if there's a general principle here, it's like using a collection of building blocks where their sum is greater than the constitution of the parts. right? In other words, there are more operations that you can build these from these things than might first appear. And in this particular case, this is just a nice, clever trick to say set register 1 equal to whatever the value in register 5 is. Okay, so in this particular case, register 1 is loading in the value of register 5. And remember, register 5 is equal to P. So what this is saying is at this point in time, register 1 is equal to P. So register 5 was P, register 1 is equal to P. So this is a complicated way of just saying, take the value of P, set register 1 equal to it, and then we're able to carry on. All right. Then the next thing we're going to do is to say 2.8 is, and you might say, well, what happened? I thought register 1 stored A, and we're kind of right, but we're going to remember also, so we've overwritten that, but we're going to remember I can grab it from the memory anytime I like. This is a little bit roundabout because I had the value of A and then I've kind of forgotten it, but I can always go in and get it anytime I want just by saying load from memory address 1 the value that you care about. So this is setting, in other words, setting register 2 equal to A because it's loading it in from memory address 0, 1. Where was that? We had it in main. So we're assuming that in main, this value of A is stored in memory address 0, 1. Then what we want to do is to say, well, we want to check, is P a divisor of A? And I could have all of that code here, but it makes a whole lot more sense because I'm going to call this on to see if P is a divisor of B as well. It makes a whole lot more sense to call a function, and that function is going to exist. So it's going to be an isDivisor. Make it one line. isDivisor function will go at address that we need to establish, and I'm going to just say is memory address 40. And I also need to say, well, it's going to have a return address. It's going to be register 7. The reason why is I've already called the minimum. I use register 7 for it, but I don't need it anymore. So I'm going to say register 7 is going to be our return address here. That's going to save me a little bit of space. And then the output I need to agree on too, and the output's going to go to register 3. Again, there's no rhyme or reason to that, but that's just what I need to agree upon for the isDivisor function. So once I know that that's the case, I can call this function with F740. I'm going to remember where I need to come back to in register 7. In the meantime, so this is our function call to isDivisor. And it will check if P is a divisor of A. I don't have to worry about how to write that function. I just know that it's going to, this function should return 1 into register 3 if P divides A, and return 0 into R3 if not. So if P is a divisor of A, register 3 is going to be equal to 1. Otherwise, it's going to be equal to 0. That means I now have an answer. I've pushed this. I'm sort of, again, delaying, structuring my procrastination, and assuming that the subroutine is going to give me what I care about. And then in the meantime, I'm just going to say, well, it's going into register 3. That's all I really care about. And so I can check and say, if register 3 is equal to 0, then I know that P can't be a divisor of A and B because it's not a divisor of A. So I will check to say, is it the case? And let me say, this is 2A. Is it the case that when I check register 3, it's equal to 0? And if it is equal to 0, I need to go somewhere else. So I'm going to jump to some other place. I'm leaving this blank just as I left this blank because I don't know where I would go yet. And so in the meantime, I say, if I make it here, I haven't jumped. And so I know that P is a divisor of A. And if P is a divisor of A, now I just need to check if P is a divisor of B. And I'm going to do that with the subroutine call too. So I'm going to have basically the exact same structure of code that I had before. I'm going to set 2B is equal to 1150. This sets register 1 equal to register 5. So this says R1 equal to P. It's the same call that we had up here. And then the next line of code I'm going to have is to say A202. So this sets register 2 equal to B now. Before it was equal to A. So I've loaded it in from the RAM to say R2 is equal to B. I can make my function call again, which is what I did here. So I'm going to say F740. Register 7 is not needed at this point in time, so I can use it again as the return bookmark that I want to use. So this is the call to isDivisor of P and B. And P is in register 1, B is in register 2. We're going to remember that when we make this function call, register 3 is going to contain 1 if it is a divisor, and 0 if it's not. So at this point in time, when we make it to 2D, if register 3 is equal to 0, it's not a divisor of B, and that would be bad. So jump to the same place as I would have jumped here. Okay, and so we will jump to a no part of the for loop. And I'm going to say jump on to the no part. So this is where we're concluding that it's no. And I'll say 2E is C3 question mark question mark. So it's going to be the exact same line that we had here. Whatever these two question marks are, they're the same as what we see down here. The point is, if we make it here, what do I know? Question for you. If I'm at line 2F, what is it that I know I can conclude? BZ says it's a divisor. We know that if we make it here, we're a divisor of A. If I don't jump in this line, I know it's a divisor of B. So that means it's a divisor of both. So if I'm at line 2F, well, what action do I need to take if it's a divisor of both? I come back, I look at my pseudocode. I want to set D equal to P. And we might remember, P is stored at register 5. Okay. D we stored somewhere else. So the GCD I said was stored at register 6. I moved it kind of to register 6 so we could use registers 3, 4, 5 earlier on. But this was our starting value of D. So I want to set, at this point in time, here's where we get to set D equal to P. And I can do this with that same trick that I just showed you to say add, set register 6 equal to the sum of register 5 and register 0, which is 0. So all this line does is sets D equal to P, because P is register 5, D is register 6. So D's value gets updated to P, and we're in good shape. Now we know what this part of the code should be. This is the not a divisor part of the block. So as we go through the loop, we continue looping. There's a part of the loop where we say, well, here is the point where I was able to conclude that the current value of P is not a divisor of A or B or both, but now I have an answer to what should go here. It's 3, 0. So this jumps to our no part of the code. And now this should be 30. And now I know that 30 here, which is the next line, as we keep counting up, the next address after 2F is 30. When we make it here, I know that what is it that I do in the no part of the loop? And it's also the part of the loop after we set d equal to p. So in either of those cases, I want to take the same action, which is I want to increment p. So at this point in time, add 1 to p and restart the loop. So we go back and we may perform our check again. How do I add 1 to p? We don't have a constant equal to 1, but you remember I made a trick, which is when we have a loop like this, I just said register 8 is always going to be equal to 1, and I'm not going to allow my subroutine isDivisor to overwrite it. So when we call this, I need to remember that register 8 can't be changed. It needs to be equal to 1 the whole time. And if it's equal to 1, I'm going to say 1558. So this will set register 5, which is our p, equal to p plus 1. And that's all that really is doing, because remember, register 8 is 1. Then we jump back. So I want to jump immediately back to where the loop started. And the loop starts all the way back here. So at this particular position, notice that p has gotten 1 larger. So p is continuing to increase as I carry on. And we're going to continue increasing p until it exceeds m. But at this point in time, I want to go back and I want to perform the checks that I have, which is to subtract m from p, so p minus m, and then I'll perform this check. So I'm jumping back to 2.5. Now I have a jump, but I have to jump to a register. So there's a little trick that I can perform. And that little trick I'm going to perform is to say, if register 0 is equal to 0. So we can check if a register is equal to 0. What do we know about register 0? It's always equal to 0. So when we see C0, it's a little trick to say just simply jump to whatever the address is that you specify. So you see that this gets commented as go to 2.5. So this says restart the loop. And the idea is if we make it here, well, the only way we could be here is if we jumped from somewhere. And we only want to jump here when the loop is done. So this is the end of the loop process. And now we answer the question of what on earth should have gone here. Now we're able to conclude that should say D932. So this is our check. Is it the case that p minus m is positive, meaning is p greater than m? And if so, jump to line 3.2 now, which is where the code should carry on. So now I can say, what do we do at the end of the loop? Well, at the end of the loop, what I'm going to do is I'm going to store register 5, which is the value of p. P is what I really care about at this point in time. I'll store that particular value of p into memory address 04. So memory address 04 is going to store my value of register 5. And at this point in time, I'll say EF00. So the function is done. I don't think this line is really all that necessary as I look at it, but the line that is very necessary is that when the function is finished, we jump to the value of the register. And why do you jump to F? Well, this is what we mean by returning. So the idea of returning is maybe now kind of connecting a little bit more, which is that when we worked with Python, you thought I'm returning a value, but we're also in this context of Xtoy, we're returning to our bookmark that we had before, and that bookmark was being stored in register F. So register F stored that bookmark, and now you're saying the function is complete. And at this point in time, the value that we want as a result of this is stored in register 6. So whatever the last value that register 6 contained at this point in time where we set D equal to P, register 6 stores our GCD. And that's pretty neat. That is the hardest function that we're going to write. So if you have any questions, let me know. We have 2 subroutines that I have to write. The 2 subroutines are going to be way shorter. The 2 subroutines do something much simpler, I think. One of them is our call to the min function. So here's our call to min. It needs to go at memory address 50. We already know some things about it. And then we've got an isDivisor function that's going to go to line 40. And we already know some things about it. Note that I made some notes about these functions as we go. All right. So I'm going to call this, let's do min2 first. After we do our trivial GCD, we already have plenty of confidence in our ability, I hope. And so now it's kind of downhill from here. I'm going to say function min2. And the inputs, well, when we called it, I'm going to say register 1 is equal to A, register 2 is equal to B, and we can see that that was certainly the case when I called the min function. And I'm trying to take the minimum of the 2 inputs, which were register 1 and register 2. So I'm going to have the same assumption there. And I also specified that the output should be register 4. So this is the minimum of A and B. And then we're going to have a return address as well, and that's at register 7. So this was something that we remembered when we called the function. We're going to jump back to register 7. Okay. I'll just tell you that the temp variables are register 3. And I'm going to use register 3, and the reason why is it's important to note that it's not actually necessary in my GCD function. So when you look at this, you see that register 3 gets used here. It doesn't really get used in other places. And that's good. So we didn't set register 3 here. We didn't, when we call the min, the min function is going to use register 3 in the meantime. But then as soon as the min function is done, register 3 served its purpose. So it's not something that's like if register 3 stored some really important value at this point in time, this would be really bad, but it doesn't. So that's something that we need to be aware of when we write it in this way. So temp variable of register 3 is completely fine. And there's an idea of the function, which is if A is greater than B, then A minus B is greater than 0. So we can use jump positive. And so our function is actually going to be quite short here. I'm going to have, we're starting this at memory address 50. I'm going to say 2312. Why do I do that? Well, this sets register 3 equal to A minus B. So register 1 is A, register 2 is B, subtract them. And now I'll say, is it the case that the result is positive? So I'm going to jump branch positive with command D. I'm going to check that register that I just set, which is the difference between them. And if that register is positive, then I'm going to jump to address 54. You might say, why 54? Well, technically it's question mark, but it's a short function, so I'm going to just tell you it's 54. And if A minus B is equal to R3, which is greater than 0, jump. In the meantime, if I'm here, well, I know that A minus B is not greater than 0, so A minus B is less than or equal to 0. So A is less than or equal to B, and A is the min. So I didn't jump over it, and that means that I want to set register 4 equal to register 1. So 1410, why do I do this? So the output is equal to A. Register 4 is what I want to return. I'm just setting it equal to A. And then what do I want to do? Let's stop the function. E700 is line 5.3. And this says return. So I've set the output variable equal to A. And then I've just said, go back to wherever the bookmark was that you had left for yourself. And the function is over. If I'm here, this is because A minus B is greater than 0 because the function has returned if I'm in this part of the code. And so if I make it here, this is where I jumped to. And I'm going to do something very similar. I'm not going to do 1410. I'm going to do 1420. So this sets the output equal to B, which was register 2. And then I'm going to do the same thing, E700. Okay, so this is our return. So if A minus B is greater than 0, what do we know? Well, A is greater than B. So B is the minimum. And as I said, that function is just way shorter than our original trivial GCD function that we were writing. It just takes the minimum of 2 numbers. And it should give us confidence that when we write isDivisor, it's going to be the same type of story. All right, let me know if you have questions. Otherwise, I'm going to carry on and show you isDivisor, and then we're done, and I can actually run this. If you have them, let me know. I'm going to specify, I'm going to write isDivisor. So I'll say our input to isDivisor is when we called it, at this point in time, it's going to take register 1 and register 2. So register 1 is going to be our P. Register 2 is going to be whatever we're finding if P is a divisor of. So in this case, it's A. In this case, it's B. It doesn't matter. We have 2 integers as input. There are registers 1 and 2. And then our return value is going to be in register 3. So that's going to be a 0 or a 1, depending on whether it's a divisor. If it's a divisor, it's going to be equal to 1. So register 1 is equal to some number P, and register 2 is going to be some number X. And R3 is going to be equal to 1 if P is a divisor of X. Else, we're going to set R3 is equal to 0. And our return address is going to be 7. The point is, what's the idea of this function? What does the idea of this function need to be? And it's a question for you, which is, how might this function work? We're going to take 2 integers as input, P and X, and I want to be able to return 1 as like the light switches on if P is a divisor of X. Otherwise, I'm going to switch the light off and register 3 is going to be equal to 0. But we need to do something to get to that point, right? Like we need to reach the point where I can know what the value of the light needs to be. But in the meantime, how am I going to get there? Like what idea could we apply to try and determine if P is a divisor of X or X is a multiple of P? Any ideas? Given the operations that I have access to. If you want a hint, what does it mean for P to be a divisor of X? If we were doing this in Python or another language, it's a more modern language, how would I be thinking of P being a divisor of X? What would be a quick check for that condition? We need to do division, of course. Sure. But what is division, right? So we know that, yeah, we need to take a modulus or take a remainder, and if the remainder is 0, then we know that p is a divisor of x. Okay, but that's a remainder when what happens when we do a division. So then the point is, we can only really answer this question if we can perform a division. But then then that means that we need to know, well, what is division really? They taught you multiplication is something, I hope. Multiplication is repeated addition. But division then is repeated subtraction. So AKB says, good. Keep subtracting p. So if I had the number, I don't know, 42, and I wanted to say, is 7 a divisor of 42? I didn't have access to anything other than addition and subtraction. I could figure that out by saying 42 minus 7 is 35, minus 7 is 28, minus 7 is 21, minus 7 is whatever it is. And I keep carrying on, and eventually I get to 0, or I don't. But if I hit 0, then I know that p is a divisor of x. And if I ever hit a negative number, then I said, well, I didn't hit 0. I wound up at a negative number. And so I will keep subtracting p from x until we hit 0, and we're going to return 1. Or we hit a negative number, and here's where I'm going to return 0. So I can check for negativity. I'll just check the opposite of what I care about for positivity. So I have a control command for that. Now I just need to write it. And here's where the mathematicians are going to call. So if you remember at the very beginning of the course, we wanted to write these math algorithms, and the whole idea was the mathematicians kept calling us back to say, well, actually, technically, there's all these cases that you need to worry about. And one of those cases is 0 is not a divisor of anybody. Okay? It might seem like, shouldn't 0 even be a divisor of itself? And the mathematicians are going to say no. So if you have p is 0, we're going to return 0 immediately. So I can do that by saying at line 40, is register 1, which is storing p, is it equal to 0? This is my branch 0 command. And if it is, I'm going to go to some particular place. So this is where I'm going to say, go to no, and flick the light off and return 0. But I don't know where that needs to be. So in the meantime, I'm going to say, let's carry on. So the first thing I'm going to do is set R3 equal to something, and I'm going to set it equal to 0 as a default value. So if I don't change it, basically flicking the light off, and if I never change it, then I'm going to return off. If I want to flip it on, I'm just going to set it to 1. So I'm going to set register 3 equal to 0. So R3 is off by default. Another check when the mathematicians call back is they're going to say, well, you checked if register 1 is 0. You probably should check if register 2 is 0. And if register 2 is 0, so if x is equal to 0, everybody is a divisor of 0. So at line 42, I'm going to say C2 and then something else, XX. So this is jump to the yes part. So here we're going to jump to no. Here I'm going to jump to yes. And until I write a little more code, it's not going to be clear where those yes and no parts are going to live. But now it's time for our main loop to keep subtracting x minus p. So I'm going to subtract x minus p, then I'm going to subtract p again. Subtract p again. So I should say p from x. We're going to start at x, subtract p from it, subtract p again, and continue subtracting p from x until we either hit a negative number or we hit 0. So it makes sense to say, let's do a subtraction, set it into register 3, and set register 3 equal to registers 2 minus 1. So this is register 3 equal to x minus p. So x is going to change as we go. Starts off at x, then it's going to be x minus p, then it's going to be x minus p again minus p, and so on. Once I do that, I'm going to say, is it the case that register 3 is equal to 0? And if so, this is where I go to the yes part. So this xx and this xx is going to be the same thing. So this is jump to yes, because register 3 is equal to 0. So if as a result of doing this, you hit 0, great. You know it's a divisor. So I'm going to just name this YY so you can see the XX's are the same and the YY's are different. So that's the no part. Meanwhile, I'm at 4, 5. And if I arrive here, I know something. So if I'm here, well, R3 might be greater than 0, or it might be less than 0. So the first thing I want to check is, what if it's greater than 0? So I can check if something's positive with the D instruction code, and then I'm checking register 3, and then I want to go to some other, particular place. So I'm making this check, and then I want to go somewhere, and now I've got a ZZ. So I'm going to jump to some other part, and in the meantime, if we're here, well, we know what? What is it I know if I'm at line 4, 6? Remember you said R3 is less than 0? Okay, great. Why do we know that? Well, I checked if it's equal to 0 here. I checked if it's positive here. And if I make it here, I know that it's R3 has to be negative. And if R3 is ever negative, remember that's where I keep subtracting P from X. If it ever hits a negative number, so P is not a divisor. And if P is not a divisor, well, this is going to become the no part of the code. So I want to say 7300, which I already kind of had set a default. So I'm just going to ignore that I did that and then set it again. Maybe it's one extra line of code. It at least helps me rest easy. Okay, so this says the light is off. And at this point in time, I can conclude that we're done. E700. So the light is off and we can return. The other thing that's nice about that is, remember, we've already had a part of the code where we said, well, there's if register 1 is equal to 0, then we know that the answer is just no. So it's not a divisor of anyone. And now I know where to jump this thing. I'm going to jump it to line 4, 6. So this is our go to no and return 0. Now I know where to jump to. It's just line 4, 6. It's tempting to put the yes part here, but we need to remember that we're not actually finished with the loop. So when we subtract R3 is equal to whatever the current value of X is minus P, this is jump to yes if register 3 is equal to 0. But there's another point, which is, well, what if it's positive? And if it's positive, here's where I'm going to put what happens if it's positive. So this is the positive part, and now I'm going to say at line 4, 8, this is the case that register 3 which is equal to the current value of X minus P, is greater than 0. And if that's positive, well, keep looping. So line 4, 8 should say, to keep looping, go 1, 2, 3, 0. So I'm setting register 2 equal to register 3. So this essentially says X, register 2 is equal to X minus P. So we had set it here. Okay. And this makes the subtraction again. And once I've done that, what do I want to do? I want to jump back. So here is, we've set register 2 equal to x minus p, and then we're going to carry back on and perform this step. So I will simply say, if register 0 is 0, which it always is, jump to line 4, 3, and jump back to 4, 3, and loop. So that will allow me to continue going. And there's only one other thing that we have to do. The final case is we forgot to say, well, what's the yes part of the code? And we wanted to jump to the yes part in this particular case when register 3 is equal to 0. We wanted to jump to the yes part here, and now I can say, well, I know it has to be a 4a. So I can fill in these xx's as 4a's in each case. 4a there and a 4a there. And now I know I'm in the yes part of the code. Okay, I'm at 4a, great. What do I want to do? Turn the light on, 7301. And once the light's on, what do I want to do? E700. This is return. So flip the switch on and return. And lo and behold, here's our code. Main starts at 10. Trivial GZD starts at 20. And it goes past 2F to 30. Is divisor starts at 40. And min2 starts at 50. So we didn't use 6, 7, 8, 9, A, B, C, D, E, F, right? There's going to be some addresses that are just blank, or that we could use to store values. Fine. What should we do? We've written the code. What should we do? Run it. Okay. I think that's a reasonable thing to try. Let's try running it. So how can I run it? Well, I could give it some values to standard in. And I could give it 1 and whatever my favorite number is. I don't know, 9. And then I could come over to each of these parts. Just going to change this refresh rate to 1 for a reason that you're going to see. But it's really pretty because, first off, I hope this is right. I hope that when I call the trivial GZD of 1 and 9, it should return 1. And, we can step it through. And we can go through and literally see everything that happens. So we read in 1 into register 1. We read in 9 into register 2. We store them into memory. And you can see that happen. So notice that they got set equal to 1 and 9 at these two locations. And then the function call is going to happen. So we step again. We see it goes to line 20. We set register 6 equal to 1, right? That's our value of P or D. Then we call the function F750. This is trying to get the minimum of the two values. And then the minimum executes. And in this particular case, these are our two things we're taking the minimum of. And it's able to return that minimum in register 6, which is equal to 1. And we can step through literally everything in our code. And we can watch, this thing go through. And now it goes to 40 and it computes is divisor. And then it's got the is divisor here of 1 and 1. And then it goes back and it kind of, checks again and carries on and so forth. So I will leave it to you to follow this through and watch the flow. And you can watch how the registers change. And I think you get about as good of an understanding of what's going on underneath the hood of a computer as you'll ever have if you step this through and watch it. I'm going to let it run though. And what you're seeing is register 2 is going to continue going down. So this is the value that we have. And then something gets printed out. All right. And in that particular case, the value is 1. We should also probably do what? Okay, let's remove this. Maybe it just returns 1 all the time. That would be bad. So let's have a value of 6 and a value of 9. And we're going to go back and we're going to reset it and we're going to run it. Now, the GCD of 6 and 9, so this is our A and B. Note that registers 1 and 2 are getting overwritten here a little bit as we go. So they're not permanently going to store A and B. Those values are going to be in memory addresses 0, 1, and 0, 2. So if you ever need them, that's okay. But all these registers are continuing to get updated. The process is going. You can see all these function calls were in isDivisor now. All those function calls are happening. The flow of the program is the same. And then we get down to 0003. It's quite something to see, right? Because we're still doing programming. Let's give it something a little bit more complicated. So let's give it, I don't know, let's give it what the numbers that we think of as 24 and 18. And I've literally just grabbed these from our test data that we had when we have in our practice exercises to follow along and make sure that our code is working. I just took the exact same tests. So the tests we had were 24 and 16. 24 and 16 give a GCD of 8. All right, great. What are those numbers in hex? Well, 24 is 1, 8, and 16 is 1, 0, of course. And so we're going to go to the run part of this and run it again and watch it progressively execute. And if we start giving it really big numbers, obviously we don't want to watch this process, but I think it is certainly mesmerizing from some perspective to watch all these kind of functions get called and all this cycling happening repeatedly. And the symphony of what ultimately is going on is just ones and zeros getting flipped on and off in different places in our computer. Because remember, hex is really just a representation of binary. So when you see all these hex commands or hex codes, they're really just 16-bit binary numbers. So everything here is just ones and zeros. And yet at the end of this process of all these lights that are switching on and off, notice that's one of the things that's nice about this Visual X toy is it is literally showing you the instruction as a sequence of lights that are on and off. We represented the computer just as a bunch of switches. So you think, well, if everything's happening as transistors, ones and zeros deep inside the computer, here's an illustration of that process happening. Pretty neat. You're seeing register 1 continue to kind of tick upward. So we're trying larger and larger register 1s. And at the end of the day, we return 8, which is indeed the GCD of 24 and 16. So we should feel pretty good. And I don't know, the last thing I probably should do is to go into a different mode here. And I can change these settings. So these settings, I can change the refresh rate to be really high. So that's only going to update me every 10,000 steps. And if I run it now, it will just do it basically instantaneously. So it's saying the clock period is about a millisecond. So it's taking about 0.872 seconds if the amount of time that it takes to do one collection of operations as the clock goes through. What the clock is doing in every cycle is able to switch ones to zeros or vice versa. So it's basically able to do kind of like one collection of operations. As it's doing that, this is taking 868 steps. And when you look at standard out, it's giving you this value of 8, which is good. But that means it's able to do it relatively quickly. And so I can go back to the edit part of this and remove the two numbers that I care about and plug in something larger. So I could plug in one of our other test data sets when we wrote this in a higher level language is 378 and 273. So 378 in base 10, when we convert it to hex, it's 017A. And when we convert 273 to hex, it's 0111, funnily enough. And now when I come back and I run this, going to take it a little bit of time. So there's a target clock period here. And 10,000 steps have elapsed. And now we see that this process takes 18,933 steps to tell us that the GCD of 017A and 0111 is 0015, which it's kind enough to convert to base 10 and its value of 21. And we had that before. We know that the GCD of 378 and 273 is 21. So everything seems to be working. More importantly, we can track the number of steps that are taken. And I'm going to try and do this again with a clock period of 0. So now that will essentially give me an instantaneous result, but it's also keeping track of the number of steps. So keep that thought in your mind with respect to the number of steps. So we're going to ramp this up a little bit. I'm going to do 03E8, a number that probably doesn't mean a whole lot to you, but that is the number 1000 in base 10. And the other one is 07D0, a number that in hex doesn't mean anything to you, but that's the number 2000. And the GCD of these two numbers is 1000. So we should get 03E8. And when we run it, we see that it takes 74,781 steps to get me to a value of 03E8. Pretty good. We would, of course, love to do this on a bunch of tests, but we've passed all of the tests that we had in our practice exercises. So it seems like we have written a GCD algorithm, and that's pretty cool. But there's, of course, something else we should do. And the something else we should do is to look at a different algorithm. So if we go back to the very start of programming for lovers, and we looked at these ancient Greek algorithms for mathematical functions, the idea was that Euclid's approach seemingly doesn't provide any particular improvement. Yet when we implemented it in a programming language, we saw it as a huge improvement. And the question becomes, will it be an improvement on the level of assembly language too? Euclid's algorithm says, well, if one of the values is 0, return the other one. Okay. But then it's just a little while loop that says, while the two values are not equal, if they ever become equal, return one. But while they're not equal, say, if A is greater than B, set T equal to A minus B. And if that value is positive, well, replace. So if A is bigger than B, in other words, replace A equal to T. So you're replacing A equal to A minus B. Otherwise, so this is in the case that T is negative and not A is bigger than B, but B is bigger than A. In this particular case, I set B equal to T equal to B minus A. Okay, so our idea here is, I guess it should be negative T here, because in this particular case, T is less than 0. But the idea is we continue iterating this process. And at the end of the day, when A and B finally become equal to each other, then we eventually return the values. And that might not be clear immediately why that's faster. And this was the genius of Euclid, that, he recognized that even without a computer, millennia before the invention of any computer, he's able to recognize that this approach has to be faster. And we're going to see this in action, literally on the level of ones and zeros. So I will have another implementation. And if you watched our trivial GCD implementation, you're going to say, oh my God, like that took long enough, right? We needed an hour plus to implement trivial GCD. And what I want you to appreciate is not only is this algorithm going to be faster, it's going to be like beautifully simple. So we're going to have a Euclid GCD function, and we're going to have a function called main. And that function is going to do literally the exact same thing that we saw before. So when we look at trivial GCD, I am going to take the same exact code and I'm just going to copy it over. And we're going to have the same approach. So read in register 1 from standard in, read in register 2, store A and B into these memory addresses for bookkeeping. We're going to call the function at memory address 20, store the return in register F. Then we're going to come back, write register 6 to the console and halt. Everything there is the exact same. In Euclid GCD, it's also going to start at line 20. It's going to have an input of register 1 equal to A and register 2 equal to B. It's going to have an output of register 6, which is going to be the GCD of those two numbers. The return address is going to be at register F. And the temp variables are funny because I don't actually care. And the reason why is it's not even going to call any subroutines. Like, wait till you see how amazing this function is. So all this function is going to do is to say, first, check if either of the input variables is 0. If so, return the other and stop. Okay, so I will say, is it the case that register 1 is equal to 0? And if so, I'm just going to tell you where I'm going to jump. I'm going to jump to line 2C. Okay, I could add the question marks, but I'm just going to tell you I'm going to line 2C. And so here's where this is go to the return B part. And I'm also going to check C22A. And this is go to the return A part. So farther down in my code, I'm going to have positions where I'm going to have return blocks. So this is the return A block, and then I'm going to have the return B block. So the return B block is going to be at line 2C. All it's going to say is set register 6 equal to register 2. So we can do that with that clever trick of setting register 6 equal to register 2 plus register 0 with this add command. And then if I make it here, I'm going to say EF00, which means return. So we know that the return address is RF. Then we have the return A block, and the return A block is at 2A. And that's where I'm going to say 1610. Oh, not 1616, 1610. So set register 6 equal to register 1. So this says the GCD is equal to A. And this says that the GCD is equal to B. And once I've set that, in this particular case, I'm also just going to EF00 and return. That's what those parts of the code are going to do. In the meantime, if I make it to this part of the code, well, this is kind of the normal part of the code. So this is the normal part of the code. And in the normal part of the code, this is where I want to check. Is it the case that A is equal to B? So I need to perform the loop. And I can check if A is equal to B by saying, let's have a line that says subtract, set register 3 equal to registers 1 minus register 2. So this is R3 is equal to A minus B. Okay. And then we check, is A minus B equal to 0? If so, we're done. And if A minus B is equal to 0, so this says C3, so is register 3 equal to 0? And if so, jump somewhere. And it's funny, this is again kind of like the beauty of this algorithm. It doesn't matter where we go. If they're equal, then I can go to 2A, or I could go to 2C. In either case, I'm going to get the correct answer. Right? So I'll just go to 2A since it's the closer one, but it doesn't matter. So this is return A. And if I make it here, I'm in the loop. Why? Because I've checked if A is equal to B. And if A is not equal to B, then I'm going to be doing this part of the code. So I just need to implement that part of the code. And I'm in the loop. And I'll say, check which is bigger. I know how I can check which is bigger. It feels like we've been doing that the whole time. So I'll say at line 2.4, D, so check for positive for register 3. Is register 3 positive? If so, it needs to go to some particular place. and I'm going to hang on to that one. So this is the a minus b is greater than 0, so a is bigger than b. If we're here, well, a is not equal to b, and a is not greater than b, so a is less than b. And if we're at that particular point, well, I will set b equal to b minus a. Okay, b is the bigger one, so I'm going to update its value by subtracting a from it. That's what Euclid says to do. And I will say line 25 is subtract. Register 3 is equal to register 2 minus register 1. So this is b equal to b minus a. Okay. And then we'll say line 26 is 1230. So this updates register 2 equal to register 3. We need to do this in 2 steps, because really what you're setting is register 2 equal to register 2 minus register 1. And then after I do that, so register 2 is now b minus a, so this is really essentially updating b equal to b minus a. And then we want to jump back to the start of the loop. And we're going to check again. So is it the case that now that I've subtracted b minus a, is a equal to b? Where did I perform that? I started performing it here. So I will say line 27 is C022, which is just jump back up. In the meantime, if I make it here, well, this is the part of the code where we've checked to say a is bigger than b that we want to jump to. So now I know a is bigger than b here. So this is line 28. I now know I can fill in the question mark with 28. And now I know what 28 is going to be. 28 is going to say set register 1 equal to register 3. So add registers 3 and 0 together, set register 1 to the result. So here's where we say a equal to register 3, which is a minus b. And if we make it here, then I'll say if register 0 is 0, meaning jump, go back to 2, 2. So loop again. And amazingly, that's it. I mean, that's the entire code. What should we do, of course? Run it. So we're going to run it. I need to give standard in some values. Put a 1. And we're going to give it an F. Okay, doesn't really matter what we give it. Come here. We set our clock to fast. So I don't need to watch this again. I mean, I could. And run it. It's going to be quick. The reason why it's going to be quick is when I go here, I need to change my settings. Make this a millisecond. And make this 1. It's just staying in one function, and it's performing a bunch of repeated subtractions. And 1 gets returned. That might not seem like a whole lot because we're just watching the computer cycle again, right? We could have a 6 and a 9. And we could run it again. We can watch them get loaded in. But notice how much faster that was? Like it returned 3 before I could even get to the end of my sentence. And we can go back here and say, okay, well, maybe that means if the numbers have some kind of a GCD, this is going to be pretty quick. And we go back and do our example from before. So we had 1, 8, which is 24. And we had 1, 0, which is 16. And now when we run it again, here are the two values here. You can see there when we reset this. Okay, they start at 1, 8, and 1, 0. And you're just subtracting the smaller one from the bigger one back and forth until such a time as they become equal. So as you go through, that performed the subtraction. And now they're equal, and you subtract them, and you just return 8 because they're equal. It's remarkably fast. We can even see this, on something much bigger. So the idea is we're seeing the same kind of principle at play, which is we only care about fast algorithms when, as the size of the input data grow. And so when the size of the input data grow, we could go back to our example from before of 017A, which was 378, and 0111, which was 273 in base 10. And we know that the GCD is 21. So when we run it, we just watch this one function perform these subtractions, you can see how quickly registers 1 and register 2 become equal, just subtracting the smaller one from the larger one. Eventually they become 1, 5, and we return. That's our value of 21. So this would have taken forever before. I'll show you again one more value that we care about. So that, I think, we get the idea here. I can go to this particular play. Let's do the same thing actually. 017A, and we're going to do 0111. And when we ran this before, I'll just tell you, you might have a great memory. You might not, but when we ran this before, this is for a different data set. It used 18,933 steps. So that's the number of lines of code that got executed, 18,933. And then when we go to this particular case where I'm going to change the settings, I'm going to set the refresh rate to 10,000 and the target clock period to 0 milliseconds and apply. We're going to look at the number of steps that this takes. And it takes 46. 46 steps for something that took 18,933 steps before. And you think, well, maybe I'm tricking you, right? Like we should do this for the other two values that we saw. And we're going to remove the values that we have. And we'll look at 03E8 for one of the values. And then we'll look at 07D0 for the other one. 1,000 and 2,000. And in the case of the trivial approach, this is where we had 74,781 steps that these algorithms took on those inputs. And when we run this, in this particular case, it takes 19 steps. Of course, in this particular case, we're not doing a lot, right? And the reason why is, well, when you subtract 1,000 from 2,000, well, you get 1,000. So they're equal quite quickly. And you think, well, maybe, Philip, you've come up with examples that are tricky. And I'd say, well, just change these a bit then, right? Instead of 2,000 and 1,000, I don't know, we had 03E8 before. We could do 0456, I don't know, whatever that is. That's 1,110. Maybe that's too similar. 051A, okay. And that's 1306, all right? So those numbers aren't sufficiently close to each other or anything like that. But then when we come into this part of the code and we run it, it's 127 steps, where we needed 74,781 steps before. So we see the power once again, right, of appreciating algorithms, and some algorithms being faster, more efficient, more beautiful than others. This algorithm uses less code. If we're in Python, it uses less code. If we're in this make-believe assembly language, it's faster in Python. It's faster in our make-believe assembly language. It doesn't matter, what we're working with, the particular language. This principle of a beautiful algorithm being faster is going to apply in either case. And that's what I feel like really kind of brings the course back to the start. So that's it. That's the end. Except it's not quite the end. Not quite the end. I'm going to give you a little bonus. So we're going to have an epilogue. And our epilogue is going to be on a little bit of theory. So the point that I want you to take from this is that programming exists at a lot of levels, but it will always exist at the level of ones and zeros. I mean, sure, we can go to quantum computing, but I think you get my point. That it always needs to be represented in some form or fashion on a very basic level. It's an electrical machine. And that brings us to the question, right? Like, well, what does that mean the limits of this machine actually are? You could see in our Visual X toy, we're like flipping lights on and off. Literally, the simulation is just flicking lights on and off. So if we're just flipping transistors on and off, well, how powerful are computers really? And that's at odds with what we're seeing in the current era of computing, where computers are getting more and more powerful. But this question actually relates very closely, surprisingly, to a question that you might have had if you've ever done a practice exercise with us and you've ever implemented a function, which is, have you ever sat there watching your program run, not knowing if it would ever stop? I don't think you've done a whole lot of coding if the answer to that is no. So we all have had this process where we think, maybe it's going to work. Maybe it's just slow. I don't know. Let's see. And my idea for that would be, well, we could write an autograder, right? We could look at your code and test immediately whether your program would ever stop. And this is a question that's so foundational to computer science that even Alan Turing was looking at this as a fundamental question in the 1930s. You might not think it's connected. I think it's inherently connected to this at Weird Takoyaki tweet from 2018. And you might wonder, okay, where am I going with this? But it's a play on a philosophical quandary called Buridan's Bridge from a 14th century French philosopher. And you might have seen it before, but the idea is you have a discussion between Socrates and Plato. It's like a make-believe philosophical discussion. And Plato says, Socrates, if the first thing that you say is true, I'll let you cross the bridge. But if you speak a lie, I'm going to throw you into the water. And Socrates can get around this statement and kind of break it by saying, Plato, you're going to throw me into the water. This is inherently related to another type of, well, I don't know if this is really a paradox, but something that really is a paradox, which is this statement is false. And my question to you is, well, is that sentence itself true or false? What do you think? Is it true? Is it false? Why? Because it's a contradiction. Why? Why contradiction? What's a contradiction? Why is it a contradiction? It can't be true, because if it's true, well, it asserts a truth, which is that it's false. So it can't be true and false. That's bad. But if you do the other way, which is that it's false, so it's a false statement. Okay, I know it can't be true. Well, but then it would have to be true because it says that itself is false. So if it's true, it's got to be false. And if it's false, it's got to be true. And this is a paradox that kind of breaks basic logic. And it might not seem like much, but we're going to see more complicated ideas of what's going on behind the scenes here. I really like the art of MC Escher. And one of my favorite things is the thing that MC Escher himself, so MC Escher is the person who he was an artist that produced things like the staircases that would always be going up, or the water would be flowing up and then it's down and it makes this big cycle and it seems like it's always going down, but it somehow makes a cyclone on itself. And he said, of all the things that I ever made, this print was by far the weirdest one. So he already did very weird things. He said this one is #1 on the peculiarity top 10. There's a great YouTube video. Here's the link to it. You can find it. I won't take the detour to show it to you because it's a few minutes long. But it shows what he was trying to do, which is that he has a drawing of a man in an art gallery looking at a painting on the wall, and the painting is of a ship in a town, and it's a kaleidoscopic effect. So when you zoom in, you see exactly what he's seeing, which is that he's in this gallery, but the painting on the wall itself is of the town. And if you look closely in like the center of the spiral, what he actually is seeing is himself in the gallery looking at the piece on the wall, which itself contains himself in the gallery in the city, which itself contains, and so forth. So there is this like infinite self-reference. And yes, a point in the chat, AKB. Is this all about Gödel, Escher, Bach? Yes. Is that probably the most underappreciated book that is out there, because so few people can, like, it's not very accessible to huge swaths of the population, because you have to kind of appreciate the music side of things and the art side and the logic side and the math side, but it's beautifully explained. And that's another great pointer to like an 800-page long book that certainly changed my life. But we're not going to make a big detour to talk about Escher. I do want to make a detour to talk about the effect that he's getting at, because he's Dutch, and there's a famous brand of cocoa from the Netherlands called Drosti, which I'm sure I'm mispronouncing. But it introduced this effect in artwork. And the idea, this is a brand of cocoa that I think only recently you could buy it at the store in the US, but I think they've had some issues with shipping and so forth. But it's a brand that goes back like 150 years. And their branding even goes back that far, because it's so iconic that you have the woman holding the tray with the bottle of cocoa on it, and then what's on the box, it's her. And so this idea of artwork that contains itself, which MC Escher's print gallery was an example of, is called the Drosti effect in its honor, because it's the first kind of like widely known example of this as an artistic effect. So I'm going to use this particular type of art to explain to you a concept, which is there are certainly two types of paintings or prints or artistic renditions in the world. There are pieces that contain themselves, so there are Drosti effect pieces, and then there are ones that don't contain themselves. And I want you to imagine that there is a trillionaire out there. What a ludicrous thing that there could be a trillionaire, but imagine there's a trillionaire and they hate Drosti effect paintings. And as a result, this trillionaire decides to start their own museum. So the trillionaire likes art but hates Drosti effect paintings, and what they're going to do is they're going to put all of the paintings that are not Drosti, that do not contain a representation of themselves, in the entire world. So from professional pieces down to drawings of children, and they're going to go into some huge open gallery. And then that trillionaire is going to hire an artist to commission, to paint a grand opening depiction of the gallery. Everybody is there. All the pieces are on the wall. And the whole idea is, we had N total artistic renditions at the start of this process, and now you've got N+1. So the question for you is, should the painting be Drosti? Should it contain a depiction of itself? So there's two options, right? The painting could not contain itself. It's just a rendition of all the paintings in this huge gallery, okay? Or it could try and do the same thing. So it could try and show the gallery, but much like Escher's work, it could try to put itself in there too. And my question for you is, well, does it matter? Is one of these things better? Or are there problems that are created by this whole phenomenon? If you need a hint, what happens if it's Drosty? And what happens if it's not Drosty? So what happens if you try to, represent itself? And what happens if you're like, no, I'm not going to represent myself. I'm just going to leave myself out of it. This one's a harder question. BZ says if it's Drosty, it contradicts the point of the museum. So the nicest thing we could do would be to say include yourself, and then we're going to hang it on the wall. But then that is bad because it's not allowed in the museum. It would be a Drosty work. The trillionaire hates the Drosty works, so that would be a bad thing to do. So it certainly can't be Drosty. We've eliminated that. But then what about on the other side? What if it's not Drosty? What happens? We can just hang it on the wall, right? Reasonable. But if it's on the wall, it's not an accurate depiction of the gallery. And so if it includes itself, it's got to be Drosty, but then it can't go on the wall. And if it doesn't include itself, then it belongs in the museum, but then it was an inaccurate depiction of the museum in the first place. So we've somehow gotten back to this circular notion. And that might seem like a silly example because it is a silly example. But if you take this example and you port it to set theory, it's called Russell's paradox. And it essentially brought mathematics to its knees in the early 20th century. So it created a huge number of problems with respect to set theory. That's, of course, a topic for another day. There is something, however, that is a connection between this Drosty effect and the Russell's paradox and what we saw before with this statement is false and the liar's paradox. My question for you is, what is it that those two paradoxes actually share? They both have something critical in common. Good. Referring to itself. Self-reference is what is shared. When you say recursion, that's also good. Recursion is kind of self-reference in itself too, right? Like you're calling yourself. So sometimes self-reference can be a good thing. Sometimes it can cause paradoxes. And in this particular case, they both have self-reference, but they're literally trying to refer to themselves. So it's art that's about itself, or it's a logical statement that's about itself, which is kind of strange. Like logic seems like why are logical statements allowed to make comments about themselves? But they also have an I am not part of them. So in other words, if the trillionaire had liked Drosty effect pieces, well, there'd be an easy resolution to the problem. The artist would come in and they'd say, we've accumulated all the Drosty works in the world, and then we're going to paint the opening. Well, I'm going to paint myself in the depiction, so it's going to be Drosty, and then I'm going to hang it on the wall. Somebody should do that. We could have the Drosty Museum. And that in and of itself, I guess, would be a little artistic statement. And this statement is true. There's nothing wrong with that. So no one has ever doubted the truth of this statement is true. So that seems to be a lot more logically sound. Of course, it's probably not clear at all what that has to do with programming, but it has everything to do with programming because we can actually make programs do some weird things. In the level of Xtoy, here's a one line Xtoy program, 8410. That's all it does. Okay, so the program starts at line 10 and it calls 8410, which we know is a load operation. And my question for you is, what does it do? You know it does something. And we're comfortable, I hope, with some X-way operations, given our entire module on assembly language. So 7410 would set register 4 equal to the value 10, because that's load immediate. But load does something slightly different. It sets register 4 to what? Actually, take a look at it. It sets register 4 equal to whatever is at memory address 10. Fine. There's nothing, that's seemingly harmless, right? So set register 4 equal to what's at memory address 10. But what's at memory address 10? Well, it's 8410. So when we run this, it's not like it's going to crash. It's going to make one line, and it's going to do 8410, and then it's going to halt. So it's not going to do anything else. But what is register 4 now? It's 8410. Okay. But then you think, well, wait, what has that actually done? From a certain perspective, yes, it's just loaded memory address 10 into register 4. But from another, when we run the program and we reset it, the program is 8410. It's kind of written the program to register 4. So it's as if what the program is really saying is write me into register 4. Line 10 is kind of referring to itself. So it's essentially saying, I have the value 8410, and this line of code that is executing right now, which is what I'm executing, is to write myself into register 4. Now, I'm not trying to say that Visual Xtoy is an intelligent being. It's far from it. But I am pointing out the weirdness that, nevertheless, in a one-line Xtoy program, you can see a little bit of self-reference. And there's two directions you could go from that. One is to say, yeah, I don't know if there's anything particularly interesting about that. It's just kind of a weird little thing, right? And that's perfectly valid. The second direction is to say, I think that this has immense impact on the entire world of computing forever and always. And that's the genius direction. And, that's the direction that Alan Turing and Kurt Gödel are going to go, because they're two of the smartest people of the last 150 years. In the meantime, I'm going to show you one more. Okay, so here's one more program, which is 84FF 9412 94FF. What does it do? There's going to be two answers. I'll give you a hint. What's the simple answer for what this program does? Well, let's see. I think it's an easy Xtoy program. Takes a value from standard in, it loads it into register 4. Okay, that's the first line. The second line is to say, put that value somewhere. So write it to memory address 12, fine. And then store whatever register 4 is to the console. So all I'm doing is I'm grabbing a value from the user, I'm putting it somewhere in the memory, and then I'm printing it. Seems pretty innocuous. And so I'm in the wrong place. So let's look at this particular thing. So 84FF. And then we're going to do 9412. And then we're going to do 94FF. So I need to give it a value, right? I'll give it some particular value. 1410. And now when we run it, okay, we read in the value. So standard in has 1410. We read it in. Oh, register 4 is 1410. Then we write it to memory address 12. And there it goes. To memory address 12. And then we're going to print it to the console. But when we try to print it to the console, nothing happens. And the reason why nothing happens when we try to print it to the console is that if we looked what happened, we took a value from the user and then we overwrote this particular value in the RAM that we wanted to have as part of our program, because we took it from the user, we stored that value in a memory address 12 to remember it, and then all of a sudden this value from the user became a command of the program. And what does that command do? Well, it adds registers 1 and 0 together and stores them equal to register 4. So it's actually setting register 4 equal to register 1, which is not part of the original intended part of the program. So we've allowed the user access to the program itself completely inadvertently, because we took the value from standard in and we wrote it over the program that we had. Again, that seems like, okay, well, that's not great. And in this particular case, yeah, we can make programs do weird stuff, but we also are going to say, let's make sure that the data and anything that the user might do is separate from the program memory, right? Like that's a very simple type of architecture. We go back far enough in computing, it wasn't necessarily standard, but this became known as the Harvard architecture for making sure that you're partitioning the instructions that you're following and then the data itself. Because those things both live in the RAM, and if you mix them, some really weird behavior is going to happen. But that doesn't mean that there's not weird behavior just in general. And we could put this particular program into something like the sandbox. And if we did, I bet you'd be, I'm going to leave that to you actually. So I would like for you to, at some point, put this program into the sandbox or into any kind of Python interpreter and just run it. And it sure doesn't look like much, but this program is an example of what's called a quine. A quine is a special type of function or special type of program that prints its own source code and exits. So when you put this into Python, what you see is that this is what is printed, this literal thing. And there are some languages where it's easier to understand why that's the case than others. This, you can actually see, here's the def main that's going to get printed, and then there's a new line, and then see q equal to, and then like there's some formatting here, and it's all very, very clever, but you wind up with this specific type of program that literally prints this exact same thing and returns. And you think, okay, that's odd. Perhaps, like that exists in any language. And it's kind of just a curiosity, right? Again, there's two paths here. There's the, yeah, it's no big deal. And then there's the genius route. And the genius route is, well, all a program is in any programming language is just a string of characters. And that's something we know from Xtoy. If you're an assembly language expert, you think of programming on the level of ones and zeros, you're thinking about the lights switching on and off. It's a string of ones and zeros. You probably, when you're programming in Python, you're probably not thinking of the program itself as just a long string. But I will point to AI and say, here's why I think of like chatbots if you're doing something like Claude code, as programming, because the program is the prompt that you're giving it, as well as any past data that you have, and all that just gets lumped together into a huge string. So at any of these levels of programming, all a program is a long string of characters. And then the point becomes, well, if that's the case, how powerful are programs really? They're only strings, and this is all inherently related to an existential crisis that mathematics had in the 1930s. So there was a German mathematician called David Hilbert, and he was a mathematical evangelist. That's probably the best way of describing him, because he felt that mathematics was essentially like the central study in all of humanity, and it's a perfect discipline, and one that will answer every imaginable question we could ever ask of it. And that entire worldview was essentially brought to its knees with one paper in the 1930s from Kurt Gödel. I am not going to take the detour to discuss this because it's immensely complicated. You can take an entire course to get you up to the point of being able to understand this. And I think there's a fantastic book from, it's like Nagel and Newman, that try to explain this, that might get you there in a couple hundred pages to build your intuition around what actually is even going on. What I want to point you to is there another genius coming along and noticing that Kurt Gödel essentially like hot-wired mathematics in on itself to explode due to a collection of paradoxes. And Turing thought, well, I don't think computer science is tremendously different from mathematics. And I wonder if I can take Gödel's work and I can also essentially like have computing have an existential crisis before we even really have anything resembling a modern computer. In Turing's case, that's the genius of what he did. In Gödel's case, he saw deeply into the fact that thinking that mathematics would be perfect was heavily flawed. In Turing's case, he noticed that we're never going to escape a certain formulation of a computer, even in his mind. If he said, we'll zoom out 100 years and take us to the point where, humans seem like they're actually very intelligent, even in that case, there are going to be problems with them in the sense that we can still do everything as a collection of ones and zeros. And if everything is a collection of ones and zeros, it's going to place limitations on what we can do. So his goal was to take this concept of a computer that we have before and just abstract away the simplest imaginable representation of that computer that we could have. So we have a CPU, we have registers, we're trading back and forth to a RAM. You might have thought when we worked with Extoy, hey, that's a really simple machine, right? But Turing's saying, I want to work with something, and his formulation of a computer from 1936 is something even simpler, which is to say we have a tape of cells. Those cells can hold 0 or 1. And they could also have like a blank state sometimes. But in the simplest formulation, the cells are 0 and 1. You have he's literally thinking of this as like an analog machine. So it's got a camera on it, that we're thinking of as the head, and then it's moving along the tape, right and left. And at any point in time, it's able to see the current cell. It can read what's on the current cell. It can see a 0 or a 1, and it can overwrite the value on that cell. But the key point with respect to what's called a deterministic Turing machine, is that the head has a number of internal states associated with it. So there are finitely many states that it could be in. So you might think of these states as like red and blue and green and purple, or A, B, C, D, E, F, G, whatever they are. Once the machine is in a particular state and it sees a value, it always has to take the same behavior. So if it's in state C and it sees a 0 on the tape, you're almost thinking of looking up a guide that says, I'm in state C, I see a 0, I'm going to overwrite it with a 1, I'm going to move one cell to the right, and I'm going to enter state X. And then I'm in state X, I see a 1, I'm going to keep the 1, I'm going to go back to the left, and I'm going to enter state Q, and so forth. So at any point in time, the head can only see one cell, and it can only move to the left or right, and then change, or maybe not change, the value that it's on and then move left or right 1 cell. So this is an immensely simple formulation of a computer that Turing came up with in 1936. However, despite its simplicity, anything that your computer can do can be implemented by a Turing machine. So by you watching this video, that can be implemented on a Turing machine. As crazy as that sounds, mathematicians have spent a lot of work formally proving this to be the case. And you might say, well, how on earth could you prove such a thing? Well, everything that the computer is doing is ultimately the result of a lot of very building block operations, which I've tried to build your intuition around by doing assembly language to say we can do GCD algorithms or prime finding algorithms or anything that you like with just a collection of a few operations. Well, if all of those operations, if they can all be implemented on a Turing machine, then the Turing machine can represent the building blocks, which can represent the larger operations, which can do anything that a computer can do. And so no one has ever found something that a computer can do that couldn't actually behind the scenes somehow be implemented by this unbelievably simple machine from 1936. And once, he starts to place computers on this formalized footing, it really starts to peel away the layers of what computers might actually be able to achieve. And I'll show you an example of a Turing machine. So we have seen binary notation, we've seen decimal notation, we've seen hexadecimal notation. I'm going to give you caveman notation, which is unary numbers or tally marks. So 1, 2 is 1, 1, 3 is 1, 1, 1, 17 is 17 ones. And nevertheless, those are numbers. So any integer could be represented with those. And I want to do an exercise. Now, you might want to go and try and do this exercise on your own or do something similar to this, and I'll leave you to it. I will show you an example of a Turing machine that can take 2 integers as input, sums them, and places the sum on the tape, right? So I'm trying to show you here is one XTOY operation, for example, a sum that actually we could perform on this simple Turing machine. Here is my idea. I'm going to assume that the head starts at the first digit of my number x, that there's an arbitrary number of zeros in between x and y, and that y is contained somewhere else on the tape downstream. So I have a bunch of ones, I have some number of zeros, and I have a bunch of ones. And what I'm going to do is I'm going to move those ones in x down to be contiguous with y. So I'm going to shift them over, and I'm going to show you how we'll eventually get the sum x plus y. In the meantime, I'm going to overwrite the x. So my Turing machine is going to have 4 states in it. It's going to have a start state, and it's going to have other states that I've tried to actually name to say, well, even though the machine is taking simple actions, I'm going to call those states different things. So state A is start, state B is move to the right until you hit y, state C is going to be called are we done? And state D is, yeah, we're not done, so we've got to head back towards X. And I will show you each of these steps. So when the Turing machine is in state A, that's start. And in this particular case, if I see a 1, so this is when the machine starts, I see a 1, and I look up the book, and the book says, well, I'm in the start state. I see a 1, I'm going to keep the 1, I have to move right, and I have to stay in state A. So I'm going to do that, and then I'm going to move to the right. I'm still in state A, so I'm in the same position I was in before. I see a 1, I'm going to keep it there. I'm going to move to the right. I see a 1, I'm going to keep it there. I'm going to move to the right and stay in state A. And now I finally hit a 0. Now that took 3 steps here. As you see, it could have taken 150 million steps, but eventually I'm going to hit the end of X. I'm going to see a 0, and if that's the case, I'm going to write a 1 here. I'm going to move right, and I'm going to enter state B. So I'm assuming that x and y are both positive, making a few assumptions here. But if x and y are both positive, what I'm essentially doing is I'm going to pull all 4 of these ones on the right over to the left. So I'm going to go ahead and write a 1 there, and then I'm going to get rid of the ones on one of the ones on the right. So the 1 here says it is now overwritten. Move to the right and enter state B. When I enter state B, as I said, I'm calling this move to the right until you hit a y. So if you see a 0, write a 0. Move right, stay in state B. Move right, stay in state B. Move right, stay in state B. Now I see a 1. I'm going to overwrite it with a 0. Move right and enter state C. So ultimately, I've been able to replace this 0 with a 1 and this one with a 0. Now I'm in state C, and I'm at this particular position, which is a 1. And I'm going to say, well, state C is going to be called are we done? I don't see a 0. If I ever see a 0 there, I'm going to halt. What this means is there are remaining digits of y, my second integer. So I can see that they're there. I know that because the machine can see a 1 here. So I'm going to keep that 1. I'm going to move left, and I'm going to enter state D. So that 1 remains. Now I'm in state D. I see a 0. And this is the go back towards X state. So I see the 0. I'm going to write a 0. I'm going to move left and stay in state D. You notice that a lot of these states kind of just stay inside of themselves until they hit something different. And now when I see a 1, I'm at the right edge of X. So I'm going to keep that 1. I'm going to move right, and I'm going to enter state A, but state A is my start state. So I kind of have brought it back to the top. What do? I see a 0. I'm going to write 1. I'm going to move right, and I'm going to enter state B. And you see that we've looped. You thought that even with Turing machines, we're not going to see like a for loop. And what are we doing? We have a for loop or a while loop that's while there are any digits left in Y, we're going to keep going through these states. So I see a 0, write 0, move right, stay in state B. I see a 0, write 0, move right, stay in state B. Finally, I see a 1. I cross it off to a 0, move right, enter state C. I'm not done because I still see digits over here, so I move left, enter state D. And I went the wrong way there. Move, and so I will loop back towards X. So the looping continues, and I'm back to my start state. So I head back towards Y. I write a 1 at the end of X. I enter state C to say there are still values left, and I go back. Finally, I'm at the end of D. I see a 1, write 1, move right, enter state A. And I'm back to the start. There's just one difference. I'm going to write my 1. I enter state B. I continue going to the right. At this point in time, when I see a 1, I'm going to write a 0 over it, move right, and enter state C. But notice, every other time I enter state C, I hit a 1, but now I hit a 0 because I've used every digit of Y. And now that I see a 0 at that position, we're just going to halt. Lo and behold, what happened? I moved all those 1s over to the left side of the tape. And I could add more states to kind of, I don't know, take me back to the start. But that wouldn't require a whole lot. So instead of my halt state, I could add a couple more states to kind of push me back to the starting point. But at the end of the day, what's happened? We started with 3 1s on one side of the tape and 4 on the other. And now we've got 7, and everybody else is equal to 0. So we've been able to represent a simple addition on a Turing machine with just 4 states, which is pretty cool. In turn, that means any building block operation a computer can do can be done on a Turing machine. And there's, in fact, a hypothesis here, which is that anything that any machine could compute is computable on a Turing machine. And that's a very strong hypothesis that has never been disproven. No one, even the most powerful AI algorithms or machines, have not gone beyond this. They've never been able to, free themselves from operations that are being done behind the scenes as 1s and 0s, which means that they've never been able to free themselves from Turing machines. And it's a very strong hypothesis because it's not just saying that your laptop or your phone can be represented as a Turing machine. All that has been established mathematically. That's all true. It's saying that any machine anybody might ever come up with applies to this. The Turing machines can replicate them. Quantum computing, whatever it is that you might come up with. Even in millions of years, any computer in that formulation of the world would also be ultimately replicable by a Turing machine. So that's weird. And if Turing kind of appreciated this, right, this is like why his work was so foundational and what he was trying to get at, which is if everything a computer can do can be done by a Turing machine, does this mean that there are problems that computers can't solve? They must have limits. They're just 1s and 0s. And that's a great observation. I'm going to frame one particular type of problem as one with a binary result. So I'm going to call that a decision problem. That's a computational problem whose output is either yes or no, true or false, 1 or 0, on or off, light switch on or light switch off. And we've seen computational problems like, is this number prime? Yes or no. So input, integer, output, yes or no, depending on whether it's prime. I'm going to give you a slightly different question that also has a yes or no answer. And the question I want to give you is, the input is a Turing machine as well as the initial contents on the tape. So the Turing machine is the set of states and rules and all that stuff. The initial contents is what is printed on the tape when the machine starts. The output is going to be, well, when we run this program, this Turing machine, with that initial contents on the tape, does it ever reach a halt state in a finite number of steps? Or does maybe it get stuck in some kind of infinite process that prevents it from halting? Notice how similar that is to my initial question, which is, does my code stop? So it's a lot like, it's equivalent essentially, because Turing machines are equivalent to everything your computer does. This question is equivalent to saying, well, I have your code, it's some function, and I have some input that we're trying to test it on. And I want to say, is it the case that this function ever stops? So when I run f of x, does it ever stop? That's the problem that I ultimately care about, like what we would love to design as an autograder. The question becomes, what we're looking for is this program. So this program is called terminates f and x. If when you plug x into the function f, if it halts in a finite number of steps and finite number of time, then this function is going to return true. Okay, so we want to return yes or no. So what we want is we want to take both of these things as input to another function terminates and return either yes or no. Does it halt or does it not? Perfectly reasonable function to write. If we were writing an autograder for your code, this is the function we would want to call. It takes a program and it takes an input. Notice both of these things are txt files, right? And I've tried to change your brain a little bit to think about the program itself as a string, which we know it's a string. So this is a string and this is a string too. So terminates takes two strings as input. It returns a Boolean value. And my question to you is, okay, as we near the end, even though the end seems nowhere in sight, how is it that we might write a function like this? Like, how would you imagine if we were going to write an autograder? What would you tell the autograder to do to check to see if, when you try to have the input x to the function f, that this is ever going to halt in finite time? How would you implement such a thing? What could we do? You got to tell me. BZU said, no matter how long you wait, you could have waited a little longer. I think what you mean by this is you could just run the code. So I could try to run your code. Like, it could take your function, it could take the input to the function, and it could just call f of x, and it could just start a stopwatch. So that's fine. But you say that's flawed, right? Because even if I wait for 1,000,000 years, your code could be so bad or so inefficient that it's going to stop, but I can't be 100% sure that it's not, it's just about to stop. Okay, so it might be 1,000,000 years in 1 minute. And so there's no amount of time I could wait for and be 100% sure that the program isn't about to halt. So ultimately, running the code is no different from you running the code and looking at the window and thinking, do I need to stop it or am I just running it, right? These days we have another answer. And the other answer is, oh, I could just use a AI approach, right? Computers are smarter than us now anyway. We could just train a computer in some fancy AI approach to read program code and analyze whether it had some flaw. You might have thoughts on that. The tools for this have gotten really good at certain types of things. So if you give it code that's very bad or with an obvious infinite loop in it, okay, it probably can analyze that. Like if you had a while true and it was at the start of your code, in the simplest case, the while true at the start of main and it doesn't do anything, well, it's just going to loop there forever. So that's an extreme example of how you could perhaps look at code and then analyze it via a meta-analysis. As AI has gotten better, it's gotten better and better at making these types of analyses. So we might feel very confidently about it. And yet, Turing showed in 1936 that this magic autograder that would take your code and take input to it and determine whether or not there's an infinite process in that somewhere is actually not a solvable problem by any computer. So he says there is no program whatsoever to solve the halting problem. And the approach I'm going to show you is called proof by contradiction. So I'm going to assume that there is such a wonderful, beautiful autograder that takes two things, your code and the input to your code. And I'm going to show you, well, if it exists, if that function exists, here is a function that takes a program as input. Now, the name of this function probably should lead you to start thinking certain things that maybe I'm about to trick you. Because the name of the function is going to be called paradox. All paradox does is takes a program, z, as input. There is a while true, which probably looks a little bit scary. There's only 3 lines of code here. While true, it's going to say, is it the case that terminates of zz is false? And if it is, I'm going to end the program. Now remember, the first question I would have is, what does it even do? I've asked students this question for a long time. It's literally 3 lines of code. And a lot of times students will be like, I have no idea. And we say, well, okay, good, right? And that just shows that even now, even after you've gotten to this point, you can find, here's a 3-line program that can be really challenging. So my question to you is, first, before I get into the weirdness of it, what is it exactly that it does? And then I'm going to have a follow-up question for you, but somebody's got to tell me what it does. BCs, what does it do if the machine terminates on the string representation of itself? So good. Terminates of ZZ means something very specific. It means that, and part of why I wanted you to think about Quines and weird exploit programs and these sorts of things, is you could imagine that if the program is a string, and well, it could also be input to itself. And most programs are not going to be particularly interesting when you do that, like to plug our source code in as the input to the function. But I said a program's a string, its input is a string, so you could imagine this is at least possible. And Turing went to great lengths to show that it is possible, okay? But the idea is, yeah, it's like Z of Z. What would happen if you plugged a program's source code into itself? But the question is, well, it would either halt or it doesn't. There's only one of 2 possibilities there. And so if it did halt, then the program's not going to end. So if it were the case that you plugged Z into itself and it never halted, then this particular program is going to end. So it's basically like it takes a program as input, and this particular function halts exactly when Z running on its own input doesn't halt. So that's the case that terminates of ZZ is false. When you plug Z into itself and it does halt, this program runs forever because this if statement never is encountered, and otherwise it's just a bunch of while truths. So this while true just continues going. There's one more question as we near the finish line, which is, okay, all right. Well, paradox is a function, right? So what about paradox of paradox? Paradox is a program. Z is a program. I'm going to set Z equal to paradox. So that means I could look at paradox of paradox. And then the question is, when does paradox of paradox halt? Remember, paradox of Z halts when Z of Z doesn't halt. And it runs forever when Z of Z does halt. And now we just write everything out. So I take everything here, and when I put a paradox there, I put a paradox here, I put a paradox here, and a paradox here, and a paradox here. So paradox of paradox halts exactly when, paradox of paradox doesn't halt. And paradox of paradox runs forever when paradox of paradox halts. So all I did was replace Z with paradox and get that it halts exactly when paradox doesn't halt, and vice versa. And now everything is very strange, because that would mean that if this thing halts, then terminates a paradox must be false, and then paradox of paradox doesn't halt. And we're right back in the same circumstance that we had before, where one direction of this being true makes it false, and if it's false, then it must be true, and we've gotten no further. Even though computers seem like these immensely powerful things that can solve any particular problem that we pose of them, they're still falling into the same traps as before with respect to Rosti art and Russell's paradox, or the liar's paradox, or any of another collection of paradoxes that all arise from self-reference. And it's tough because we're seeing computers do progressively more amazing things. So in every generation, there's the person who says theory doesn't matter, right? Like, who cares about Turing, because look at what the machines can do for us. And it seems like this halting problem proof is nothing more than, some weird self-referencing that we can just shoo aside into the corner, and we don't have to worry about it. This is a literal post that I got from Stack Exchange. Rest in peace to that platform. And somebody fortunately came along and said, we still need to study theory. It's still an important thing. And they said the reason why is because there's so many practical problems that don't seem like the halting problem, but they are the halting problem. And if you solve one of them, then you would solve the halting problem, which means you can't solve them because you can't solve the halting problem. You have a programming language, and you want to convert that into machine code as efficiently as possible. This is an inherent problem with Python, because Python has presented to you, the user, the human user, this beautiful interface. But the conversion of it to machine code often winds up being slow. So you might say, well, we could look at a different language or try to optimize it in some way so that it would give you the fastest imaginable machine code for a given problem, for a given program. Actually, it winds up just being the halting problem. Or all these questions about security or antivirus or whatever it is, and you're trying to find the best solution to this question, and it winds up being a meta question, it winds up just being the halting problem. So here's another one. I'll give you an example of something like, are these two functions the same? Input two functions. Output, yes, if they're the same, no, if not. So what does that mean? That on the same inputs, they always give you the same outputs. Here's two functions. Now, this is kind of a made up little example. I just want to show you a flavor of it. Here's two literal Python functions. H says, take a string as input, return an integer. It calls this function f of x, and it returns 1. So it doesn't seem like it does anything particularly interesting, but it does return something only if f of x doesn't run forever. So it returns 1 precisely when f of x halts. So this might take 1 billion years to run f of x, but if it takes 1 billion years, it eventually will return, and that's what h does. It doesn't matter what input you give it as a string, it's always going to return 1 if f halts. And then the question becomes, well, g certainly always returns 1, but then when are h and g equivalent? When f of x halts. So we've taken the halting problem and we kind of hotwire it into a lot of other different questions. And there's a general version of this called Rice's theorem. So Rice's theorem says any question you could make computers answer about themselves that is non-trivial and like self-referential, meta in some way, winds up being undecidable. Like there's no solution to them. There might be solutions in certain categories or in certain cases, but a general answer to this question is undecidable. And why that matters as much today as it ever has is because one of those questions is, hey, AI, are you safe? And that's like inherently connected to this foundational theoretical work that Turing was doing nearly 100 years ago. So it might not seem relevant. It's actually as relevant as it's ever been. And self-reference broke logic, it broke set theory, it broke mathematics, it broke computer science. And meanwhile, we are hurtling at breakneck speed towards self-reference being more and more pressing in the era of computing, with machines that are really getting very close to truly learning how to say the word I and mean it. And what's going to happen? I don't know. I can't pretend to know what's going to happen. If I knew, I would probably be a very much more successful person than I'm going to be, because answering that question is a very challenging one. What I can say is that I've taught the course for years, and I've loved showing students a little bit of theory at the end for years, but I've always felt like it's hard to convey just how beautiful some of this Turing stuff and Gödel stuff and Escher stuff is unless you really get your hands dirty with it. And students love applied things, and they want to see computers make stuff and build stuff, and I'm there too. I love building things. And yet it seems like this material is as important as it has ever been. I mean, heck, the Pope, literally today, the Pope put out a manifesto about AI and the future of humanism. And I looked at that. I haven't read the whole thing yet, but one quote from the Pope stood out to me. And the quote that he had was, he hopes the world, quote, will come to recognize the human heart as the place where God desires to dwell. Now, you might not think that that has literally anything to do with what we're doing here, but people have always asked me, like, why call your project Programming for Lovers? That seems weird. What are you really getting at? And I think I've given a lot of answers to that question, but from now on, I'm going to say that somehow, some way, that quote from the Pope is the answer to that question. So Programming for Lovers is now officially in the books. It was great to have you here. Thank you so much for joining me. Take care of all of yourselves, and I will hope to see you a little bit farther on down the trail.